Everyone. I am Abdul Salam Yazid from Istanbul Technical University. I'll be explaining uh, my work, which is exploiting the cross-domain knowledge of large language models in the domain of healthcare. And I am pretty sure that everyone is aware of large language models. So, machine learning has been is really popular today. Machine learning models are used in different domains, different sectors. They are used in, let's say, healthcare. They are used in advertisement, for example. Uh, these models, for example, in the domain of healthcare, they could be used for early detection of cancer and neurological diseases, for example, like Parkinson's. These models rely on dataset for training. They are being trained on a particular dataset to perform a particular task. However, the issue is that when they are trained on a particular dataset, when it comes to, in some cases, when it comes to real world applications, uh, the performance of these models can really degrade. Um, and this is due to statistical change in data. The statistics of the data set used in training these models can be very different from the distribution of the data in real world, which really hurts the performance of these models. Sometimes the data set that is being used is very, very limited, and the the classes, maybe if it is for detection of a particular disease, there could be a class that says, okay, this is a cancer patient, and this is not a cancer patient. Sometimes the these classes could be very imbalanced. Maybe there are few in the data set. There are only a few number of classes that um, are attributed to a cancer patient. And privacy also contributes to having limited data set. Sometimes obtaining this data set is very difficult. So let's look at generative models. These generative models are not just trained on a dataset on a particular domain. They are trained on dataset from really very different domains, maybe sports, politics, advertisement, healthcare, arts, science, mathematics, English, chemistry, from different domains. And what happens is when these models are trained from different domains, actually knowledge is being shared from one task to another. Uh, before, Prior to large language models, usually every task has a separate model, but these generative models can perform um, different variety of tasks. And this enables a cross domain knowledge such that one task uh, assists another. So the aim of this study is to exploit that capability of these generative models so that we could enhance the robustness for real world data sets that usually has a problem of, let's say, this statistic data distribution shift. Uh, in fact, since when you have a limit, sometimes you have a limited data set to train a particular model for a particular task of healthcare, instead of using a standard model, you can actually use a generative model and fine tune it on a limited amount of data sets. So the goal here is to really get insight. If we do this, we fine tune that particular generative model, we're going to compare it with a standard model that is just being trained on one task and one data set. so that we can see the potential of these new generative models that are very popular today. So this diagram, we go through that with, we have, as I mentioned, different formats of data that are being used for this, for the training of these large language models or generative models. And they're able to perform, let's say, image captioning, sentiment analysis, and object recognition for images, for example. So for this experiment, I have three data sets. One for Parkinson's detection. So given a set of features, we're going to predict if that particular patient has Parkinson's. And I have categorized this particular data set as a medium-sized data set. So it relies on stride interval. The stride is like the time between when a person's foot touches the ground, lifts up, and then touches the ground again. That interval is the stride interval, and that is very important for a data set of Parkinson's, for example. We also have a stroke data set to predict if a person has stroke. I have categorized this data set as small and imbalance. This issue of imbalance is very important. And there's also one virtual screening data set, and I've categorized it as large, and it's for regression. So um, this data set is for training a model to predict the docking score or binding affinity between two molecules, a protein maybe and a ligand, usually used in the domain of virtual screening for drug design. We're going to be using we're going to be I experimented with a neural network, an XGBoost model, and then GPT-4o from OpenAI. And GPT-4o here is the generative model that we'll be using. I experimented from each data set. I trained the model on 25% of the data set and 35% of the data set. And I use very important metrics, recall, precision, and F1, especially for the classification to assess the how good the models are after making predictions for a separate test set. And I also use a mean absolute error for the regression task for the docking prediction. So this precision metric is very, very important. The higher the better. And when a model has a high precision, it tells you that that model, when it makes a positive, when it says this is a cancer patient, it means that that is really a cancer patient. It is very important where you want to avoid false positive. When a person doesn't have cancer, you don't want to say that person has cancer, for example. And recall is also another metric when you need to be able to really identify a particular case. So when the model has a high recall, it means that when it says a person has cancer, um, it is able to really identify individuals with cancer with high accuracy. This is what recall is. And F1 score is the more like the harmonic mean between the precision and recall. So high F1 score means both precision and recall are high. It's possible that precision could be high, but recall is low. Both of these three metrics are measured between 0 or 1, 0 and 1. The higher the better. So these are the results for the Parkinson's. For the generative model, I obtained an F1 score of almost 0.9 using just 25% of the training data. and 0.92, F1 score 0.92 for training set of 35%, which is really the highest of all the compared to the remaining models in this Parkinson's. This stroke data set is the most difficult actually. It has limited data sets. It is a limited data with limited with imbalanced classes. And here it is the generative model also prevailed with a F1 score with an F1 score of 0.85 in the training set of AAT 25%. Similarly, very high F1 score for the training set of 35%. Both of the standard models, the artificial neural network and XGBoost did not perform well. In the virtual screening, the lower the better, low mean score. You want to compare the docking affinity between a the docking score between a ligand and a protein. And when you compute that, you compare it with the ground truth using mean absolute error, and the lower the better. In this case, and on average, GPT-4 scored the lowest. In essence, the generative model outperformed all of the um, other models. This is a summary of the results. As we can see, for example, this is for the Parkinson's detection, this is for the stroke detection, and the table 3 is the virtual screening. We can see all the models and F1 score precision and recall. For example, F1 score of the neural network here is significantly um, lower than the F1 score of this GPT-4o. And in precision, it is significantly, okay, not significantly, but 0.5 essentially means randomness in precision. Overall, I observed remarkable performance for the generative model. So, as I said, the generative model outperformed due to this cross-domain knowledge. Remember, that is what I'm trying to exploit, and it worked for this particular setting of mine. It showed really remarkable robustness for even when the dataset is limited with imbalanced classes for the stroke detection. And yes, the cross-domain knowledge can really be useful for real-world applications. So imagine if I use that particular generative model in a real-world setting, it could really be helpful and provide um, very robust predictions for a particular task. One of the issues that I faced is the cost of fine-tuning that generative model. I had to format the dataset in a natural language, and for each of the rows, for each entity in the dataset, when I formatted it, it increased the length, and the token size of the models it increased, and this was very costly. And I was not able to maybe attain a robust data set. Most of the data set I use are open source. I wish I could get maybe more robust data set from Kleenex that I could use for this experiment. So this issue limited my experiment. I would like to maybe use um, instead of using, because I use GPT-4o from OpenAI. It has a application programming interface. I could maybe try my own local on my own server, on my own maybe computer, a local generative model to reduce cost and for privacy. Also try different models, standalone models with diverse data sets. Also maybe ensemble method. There's an ensemble method where when you want to make a prediction, you rely on multiple models. These multiple models will make predictions, and then you take the average. So imagine I could use a standalone model with a generative model, take the average as a final prediction. This could also be helpful because the standalone model is being trained for particular task while you are exploiting the cross-domain knowledge of the generative model. Yeah, I think this key takeaway is a repetition, and it could be helpful in real-world application. Uh, it could really be helpful to address the current challenges for especially that is being observed in dataset to improve performance. Thank you very much.